Section 6.9 Quadratic Forms. Now we're going to talk about central conics. A central conic, remember what a conic section is from calculus. Conic section is something such as an ellipse or hyperbola or parabola. And a central conic is the kind of conic that's centered at the origin. So this one is also centered at the origin. I purposefully drew the ellipse tilted instead of like level, which is normally you see most of the time when you see an ellipse in a problem, you will see it sitting nice and level instead of tilted like this. The tilting happens right here with the value of x, y, and we will talk about how to get rid of the tilting by readjusting the coordinate system. The x and y axis, turn it in such a way, turn it just right so that the ellipse will appear to sit perfectly centered and level and all that instead of crooked. Now, I should also mention that this thing right here is called the central conic. The central conic also include parabolas, but we're not going to care about parabolas right now. We mostly care about the ellipse and the hyperbola, and certain limited in extreme situations. For example, in certain situations, the hyperbola turned out to be just two lines that's crossed, but that's not really that important. We mostly just consider our standard system and how do we adjust the coordinate system such that this thing, we can make the middle term, the value of b, disappear. So anyway, this particular equation right here, qxy equal to ax squared plus 2bxy plus cy squared, that is called the quadratic form. Now, the quadratic form isn't just limited to two variables. You can have the quadratic form in three variables, so then you will have x, y, z, and all in squares, and then all combinations of this kind of thing, two of them at a time, that is x, y, y, z, and x, z, which all have constants and so on. So you have a big list of stuff. But the principle is the same. Our goal is to eliminate this somehow by realigning the coordinate system. Now, in elementary calculus, at some point you have probably learned that in order to readjust this thing so that everything's lined up, what you do is that you turn it with this particular system of equations. You have a new system, x prime cosine theta minus y prime sine theta. And then you set y similarly equal to x prime sine theta plus y prime cosine theta. What happens is you transform x, y into a new coordinate system that is x prime, y prime by turning it by a certain angle called theta. And in this particular system, you have learned it in calculus. If you don't remember it, it's better to just believe what I tell you. Or if you do have time, you can sit down, crank this out, and verify that this is true. But to turn the system by a certain angle theta without moving it, just turning it through the center, this is the bunch of stuff you're going to end up doing. Now, the deal is that eventually, after you plug x and y into this equation right here, you will, of course, come up with a new equation that looks quite different, but basically the same form. That looks like this. You will end up with a prime x prime squared plus 2b prime and x prime y prime, and then plus c prime y prime squared. And that will still equal to k. The value of k doesn't change because all you did is you changed the way you look at this thing. You just looked at it from a different angle, but everything else is still the same. So then if you plug this stuff in here and mess around a little bit, this is what you will end up with. Now, at this point, we need to mention something very important, is you can choose theta in such a way that you can arrange this value of b prime to be 0. That can be done, well, you can also prove that if you want, or just believe what I tell you and not wear yourself out proving all those details that you've already done at one point. But anyway, the point is you can choose theta in such a way that this will be 0, which means you will end up with something that looks much nicer, which is the whole point of turning this stuff, is so that you will end up with something that's neater like this, just with only A and C values left, and the squares equal to K. And once you have this, then you can totally see what this thing you were given really is. That is all the details. For example, if it's an ellipse, you will be able, from here you can tell them how wide the semi-axes are, or if it's a hyperbola, then you can tell well other stuff like where the asymptotes are and so on and so forth. But anyway, that is the whole purpose of doing this turning. And then one more thing we want to say is that there's an unusual situation, that is, it just happens that the original value, if you calculate something called the discriminant, which is called AC minus B squared, AC minus B squared. This particular value happens to be the same even after the transformation. We plug this thing in and you get a lot of variables and you finally round everything up and you find out that this is just happens to be exactly the same as in the new case as the old. Somehow the changing, the transformation, that is turning of the coordinates, did not change the discriminant. This is called the discriminant. It can also be written in matrix form, a simple little matrix, which is ACBB, like this. Okay, the same way over here. And that thing does not change, which will be, which is a very interesting fact. But of course, you might ask, well, okay, that's fairly interesting, but why do we care about this? Because we're talking about partial differential equations here. The reason we talk about it is because this is an application of Lagrange's method. We will, with Lagrange's method and all this information that we got, we will be able to transform this from this thing to this thing with a fairly simple method and bypass the need to find theta, which is fairly complicated. Well, it's not a whole lot simpler, but it's a little bit simpler, and we will talk about that in the next video.